had one for 30 years now. It's gonna be...
Testing. There we go.
This is my third week on the road at conferences.
All right, we're going to get started. Good morning, everybody. Welcome to the second session this morning. My name's Joe Applegate. I'm a senior principal hydrogeologist from Tallahassee with Geosyntec. We had a great crowd come for the first session. They're probably going to be coming in later, but I presented last year, and I'm really happy to see so many early to mid-career professionals here. Based on all the challenges we have with PFAS coming up over the next couple of decades, we need all the new practitioners for PFAS and experts. So appreciate all the presentations and participation from our younger folks. So today's session is site characterization and managing liabilities. We have a very diverse and experienced group of speakers here with us today. I did want to point out just the observations over the last day and a half. We have a lot of challenges with PFAS, from regulatory to site assessment, remediation, legal, and funding. And at some point it's overwhelming, but from my perspective, we've all made a collective advancement in the industry. I think industry and regulations are slowly catching up to the science. We've got a long ways to go, but just in Florida, at the various levels for the federal programs, all the DoD facilities, they started assessing their PFAS back in 2015, 2016, and many of them have been through the preliminary screening, the site inspection, and many of them are in the RI stage right now. So a lot of progress has been made on the federal front. Teresa Bruchegi gave a presentation on all the progress that DEP's made. The majority of the fire training facilities have been assessed or in continued assessment. One's gone through a source removal. They're looking at dry cleaning and state sites and other sites for PFAS. So they've got challenges, but the state's made a lot of progress, and even the municipalities. I know the new bill hasn't been signed yet, but that's going to give a little respite to the municipalities. But even the folks that have gotten the 62,780 letters have made quite a bit of progress on trying to get their arms around their PFAS issues. So we're going to have a couple more years now to continue to develop the science and catch up. We have one talk on advanced site characteristics for PFAS today. You're going to hear a lot about all the different treatment technologies that are being applied to real life sites. And we're doing a better job in managing environmental liabilities for facilities that are struggling with what to do with all their PFAS streams. So we've got a lot of diverse presentations here today. So with that, I'm going to kick it off with Dr. deSilva. We are going to ask for questions after each presentation, just a couple of questions so we don't have to hold out till the end. So our first presenter is Dr. deSilva. He's a senior treatment process engineer with Freese and Nichols. He's got significant PFAS experience. He's presented over 170, prepared and presented over 170 papers on PFAS. In 2021, he got the Best Paper Award from the Air and Waste Management Association on membrane PFAS treatment. And today he's going to talk about what's new in the destruction of PFAS in water. Dr. deSilva.
Thank you very much. I'm going to talk today, give a background of what PFAS treatment systems are used before I go to destruction technologies in the United States. In the US. So there are several PFAS treatment systems that are operating right now. Some of them are like 3 months old. 6 months old, maybe a year. So I want to give you in different states what's happening. The first one I'm going to talk about California, Orange County Water District. They have high pollution of the groundwater that is provided to numerous customers in the Orange County area. So Orange County is planning about 35 PFAS treatment systems in the next few years. 3 are already operating. So this is an example in Fullerton, California. They have different PFAS concentrations coming into this ion exchange plant. It is operating still since last July, last year. 4.3 mgd average flow. They spend about $3.7 million on this. It's a small footprint, and this is a groundwater. Their water quality, the raw water quality, they did some pilot testing and decided to go with ion exchange. They have the biggest ion exchange PFAS treatment system, not this one. Right now operating, I think ribbon cutting was last in March. 11 trains like this. This one only has 4 vessels. The bigger one has 22 ion exchange vessels. This is another treatment system operating in Alabama, just started last December. 10.6 mgd, $30 million spend, and they are operating. It's a surface water treatment plant, conventional plant they have, and they had PFAS in the river water. So 3M plant that is has discharge to the surface water, and they have to treat it. A lot of this is in a town called Decatur, Alabama. The people got sick, and then they did some blood sampling, and they found PFAS in people's blood, and then the city sued the company. And then they fully paid the $35 million. They got $35 million. And then I think the lawyer's fee was $5 million, so they got fully paid for this treatment system, and it is operating right now. So this treatment system, what they did at the very beginning, they used granule activated carbon, bigger vessels to treat PFAS. And what they found out is the granule activated carbon removed the long chain PFAS compounds that is in river water, but not effectively into significant level removal of the short chain. So that they spent about $4 million about 3 years ago, and then they decided to go to reverse osmosis system. So they implemented the reverse osmosis system, and that removed to non-detect level. Now, what they did was they took that granule activated carbon vessel, and then now they are putting into the back end to polish the concentrate from the RO system. So they have a longer residence time, very low. I mean, they were not 10.6 mgd. They are only treating from the GAC maybe like 600,000-700,000 gallons a day, and they may run it for a year before they replace these carbon. So it is very well running right now. Again, only 3-4 months old. Treatment systems removing to non-detect level. Why they went to non-detect? Because the regulations are changing. They didn't want to get to like 10 or 5 or 20, because otherwise they have to do it again. So they decided to go to non-detect level of treating the drinking water. This, you may have heard about Cape Fear River. that is highly polluted because of the chemo. That's a treatment, that's a spin-off of, I believe, 3M that was discharging to the Cape Fear River and contaminating the water, surface water in North Carolina. And that has Genex in the surface water. So downstream of this, by maybe even 100 miles downstream, there are so many, number of treatment plants that have intakes from this surface water. And this is one in Brunswick County, North Carolina. Northwest plant, they are planning to add this white building here. You can see that's the reverse osmosis plant. They are going to in the capacity of about 36 mgd, they are almost that. To build that plant is $100 million. To operate is about $3 million, and it's coming up next year. Another plant on the same river, it's called Sweeney Water Treatment Plant in North Carolina. So they have to add a polishing step. For this surface water plant, existing surface water, they went with a very large granule activated carbon systems. You can see this, filter beds, like 8 of them, they are building in the existing treatment plant. Now, every water is different. They may have done some pilot testing, and they found out GAC is good for them to polish it. And they are also spending about $2.9 million on operation cost and $35 million on capex, but the capacity is 35 mgd for 8 granule activated carbon filters. Now, when these tanks, when you see the granule activated normal tank, small in a remediation site, it might have 2,000 or 3,000, or maybe smaller metal tanks. These are big tanks, maybe 70,000 pounds each. So they have a better, they can treat a large volume of raw water, and this is a polishing step, not major treatment systems. This is, yesterday you heard about 3 towns in Florida, Stewart, Pensacola area, and also Zephyr Hills, which is not far from here. So Stewart had some firefighting training facilities. There were multiple sources that contaminated. There are 4 wells, 1, 3, 5, and 24 raw water wells. And they implement ion exchange system, and then it is treating those treatment systems in Stewart, which is north of West Palm Beach. All those ones were water treatment plants. This is a landfill in North Carolina. It's called New Hanover County Landfill. I was involved in this design. It's a smaller leachate treatment plant, 75,000 GPD. $4 million we spent in 2018 to treat PFAS and arsenic from the leachate itself. And they have their own NPDES permit to discharge to the river in the backside here. So they have a lagoon here, and then a little package plant, the green here. And after that, it comes to a reverse osmosis plant inside this building. The white tanks here are the concentrate holding tanks. So they have 2 10,000 gallon concentrate tanks. And lucky enough, they have this closed cell inside, in front of these tanks. It's a closed cell covered, it's a line bottom lined, as well as top. It is a closed cell. So we did some pilot testing to inject those discharge, the concentrate back to the closed cell using about 8 shallow wells. This is just to buy time until the destruction technologies are available. And then when you inject it today, you won't see it like maybe a couple of years coming back, that concentrate to the leachate, because there's no rain. I mean, rainfall will not get it because it's already capped on the top. So it will take some time. And only thing is, when you have these shallow wells, you might get clogged some of these wells because of the salinity. So that's why we only need one well at a time. So we built like 8 different wells.
This solutions where you use activated carbon,
Ye-
it doesn't really work well for short change molecules.
Yes.
The same problem remains when you use RO, right? When you take out all these compounds, but using
Recording in progress.
for the concentrate, but shorter chain molecules remain in the reactor, right?
No. In the RO, it will take everything out.
Right, but the concentrate, the retentation.
Oh, yes, 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 yes.
Still remains. So is that a significant issue that it remains in the concentrate even after treated with activated carbon?
You mean the concentrate you need to manage separately. So long chain, short chain, everything will be in the concentrate, and you need to manage that separately. So that's a different. I will talk about what are the options for the concentrate to manage. There are several options to do it until you get the destruction. That's why. That's why we have, we are looking, I mean, in the future, looking at destruction technologies. So here, you can see this one of the wells we developed there. And then to answer your question, the deep well injection is one option. It is popular in Florida and maybe some states. There are third-party environmental companies like Oklahoma, Tulsa, near Tulsa, Oklahoma, and Corpus Christi, Texas, and then Columbus, Ohio. I mean, different places. They will charge you per gallon if you can truck it. It's expensive, but if you have a smaller amount, maybe you can truckable. I mean, not in the distance. That might be an option. And then yesterday we talked. We had a talk about cementifying, using a landfill, and then use the concentrate, and then use a cement to apply as a layer on top of a landfill. That might be an option. Also, incineration is not going to be a popular option because already New York banned incineration of PFAS because what's happening is in the normal incineration processes, the temperature that they incinerate, it just transforms to a different, maybe a different precursor of PFAS, and then it might travel up to about 50 miles. Some places they have seen the plume has traveled about 50 miles and drop into water. There's middle of nowhere, no PFAS, but it came from clouds and the plume, and they have contaminated the water body. So it is banned in some, and then we can expect once the MCLs are developed, Title V permits will be, PFAS compounds might be included on those renewals in the incoming future. So, again, something like the question you asked, this blue in the bottom in that diagram, like the Alabama case, you can use another treatment technology to concentrate the concentrate. So reverse osmosis have a closed loop type system that you can do another membrane to concentrate the concentrate, because the goal is to reduce the volume to a content, so you have less volume to be deal with. So the people are using these steps to get the volume reduction. Landfills might accept your PFAS waste today, but in the future, it's not sure whether they will accept those PFAS compounds based on what's coming up in the registration. It might, if they list PFAS as hazardous waste compounds, then it will be, you may have to travel not 40 miles, maybe 300 miles out of state to dispose these waste. So destruction technologies, I'm talking about first electrochemical oxidation. So you use a current to degrade PFAS. Have seen some electrodes like boron dope, diamond, and lead dioxide, and other probes, cathodes and anodes used. And they are producing, in these reactions, you can see they are producing the fluoride and shorter chain PFAS compounds. So maybe you have to recycle back again the shorter chains, and you can get maybe more reduction on these. Typically, the research has shown their electric energy consumption of 50 to 250 kilowatt hour per meter cube. So there are two types of electrochemical oxidation. One is called direct oxidation, where electron transfer from PFAS happening at the anode in the left side of this diagram, and then indirect is splitting the water to create this hydroxyl, very powerful radical that will react and produce these PFAS compounds to convert to fluoride and carbon dioxide. These technology is sensitive to some conditions. Dissolved oxygen carbon may need a longer electrolysis time. High temperature will accelerate the process. pH value low have been shown higher degradation, but when the pH is higher, there are some questions about corroding the anode and cathode as well. Research also has shown the sulfate may reduce. So there are some water quality parameters and environmental conditions that universities are testing right now. What are the perfect conditions? So it all depending on your water. What's your water quality parameter when you select one of these systems? Supercritical water oxidation, you can see from here the liquid water. This is finding a best envelope or the best points of the pressure and the temperature that we can get more solubility on the organic, and also oxidation process is accelerated. So the temperature has found to be 374 degrees or up Celsius, and the pressure is about 22.1 bar. So this red area is the area that is best for that, and this has been tested and was successful to destroy the hazardous waste, especially halogenated compounds in the past. So what's happening here is you can see from the diagram below the bottom, the organic waste you mix with air. You don't need oxygen, pure oxygen. You mix with air, and then in the process you have apply these conditions of temperature and the pressure, and then you degrade or break the molecule to water, carbon dioxide, and also it generates some heat. So the advantages of supercritical oxidation is it has shown 99% degradation of organic compounds, no catalyst needed, and then very fast, small footprint, can use air, so it's more cost effective. There is some scaling issues. There might be not good for the bigger systems. And then there are some issues with the salinity, if that is present. And then because we are applying high pressure and high temperature, the systems might be vulnerable for degradation. So there are 4 companies who are already actively pursuing this. Danish company, Aquadon, and then 374 Water in North Carolina, and Battle Labs is also doing research, and they have a system in Ohio and then a California company. So they are tested. There is 2 papers out right now. They have tested this method for AFFF, and it has shown some good results. This paper is just out from EPA. Max Krauss, he's the one who is actually investigation of destruction technologies. His paper in the AC journal, Environmental Engineering Journal, is published this data. You can see it's a log scale, but you can see the influent and effluent of AFFF. They have some good results for some compounds, and that's using one of these vendor technologies. Battle Labs also did some testing with, you can see the green bars. It is less than 1 compared to the 10,000 or 1,000 concentrations reduction. So it is showing some promising results. Still is in the developing stage. I would say it might take a couple of more years to get these things into the market. The plasma technology is the last one I'm going to talk. There are 2 different types. Thermal plasma technology, where our PFAS molecules are destroyed by thermal mineralization, or non-thermal plasma treatment is electrical discharge of plasma. That is creating a reactive species to decompose PFAS. If you have seen some of these results of the plasma, I think if you go to the exhibition hall, there is a poster that is results from Florida A&M University and Florida State University and Geosyntec and other entities have put together their team. And what they have found is from plasma technology, the C8 compounds definitely will be break to a smaller compound, C4. So in very fast fashion, it's 100 microseconds. So these to get it the total reduction or total destruction, you may have to have number of reactors, so one after another, because then you go from 4 to 2 and 2 to 2 carbons, and then go to carbon dioxide and fluoride. So also there is a company called Red Hill Scientific. They are already involved on a full-scale system. So that might be another technology, but also there might be issue if you are going to do like more than 100 GPM per unit. So these are still in the smaller unit, but it may be in the future it might come to a better sizing on the scaling unit. Advantages of that, plasma technology can remove precursors. You don't need any chemicals. It is effective against both short and long chain chemical PFAS compounds. Uh, and then there might be an increased energy demand if you have high salinity and also the temperature. It's also depending on those. So there are some advantages, disadvantages of each of these destruction technologies, but still they are not in the full-scale systems. So in summary, we need to keep up with the regulations. It changes. Some states have already, you have heard yesterday, have gone and they have created their own regulations, but also not only the regulations, it will come to NPDES permits, biosolids monitoring, application, the discharge methods, the air permits, everything. So you may have to plan for that. And also, you may have to take care of the waste streams if you are not destructing the technologies. Sometimes these vendors who are providing these systems, they will take care of a long-term three-year service contract that they will take care of the waste. So that's a possibility as well. And the technical readiness of these destruction technologies are vary. Some might come quicker, the others might be a little late. But there will be, I would say, within the next decade, there will be many, many options available rather than the GAC, ion exchange, and reverse osmosis, the three technologies available today. Thank you very much.
We've got time for a couple of questions, if anybody has any additional questions for Dr. deSilva.
I may have missed what you mentioned earlier about the RO units that other facilities are using right now, but what did they do with the GAC, the SPAN, the UGAC?
Okay, so you mean the spent GAC media, right?
Right. Like you use them to filter out, the PFAS and, all the contaminant.
Right.
But I think I asked similar question yesterday where, like you say also, some of the landfills are taking them, but down the road, likely they're not going to do it anymore. What do you do with them right now? How do you treat them instead of sending them to landfills?
Yes, so when you, especially on the GAC or ion exchange both, when you have a system installed to remove PFAS, the GAC has to be provided by a vendor, the granule activated carbon. So there are two options. One is virgin, the brand new GAC carbon, so they will bring in a truck the brand new load of GAC, vacuum the old one to a vessel, and then put the new carbon to the system. So that one is the cheaper one, the expensive one is the new carbon. Second option is like regenerated granule activated carbon. Typically, 99% of the time, the vendor who brings it, he takes the old one.
Right.
So I ask this question from designers all the time, and they are saying, we don't know, because they are taking it. So they have, wherever they are taking it, bringing it, they are doing something in their facility. So they have their regenerative oxidation system or some mechanism in their facility, because that's their storage. So every 3 years, typically the client or the owner of this facility, he pays the vendor nominal fee to refill and then take it out. Wherever he's taking, he might have to take to like out of state somewhere after they have a product. So we don't know yet, but the RO concentrate is a different story. RO concentrate you have to manage because that's in your facility, nobody's there. So that is the one you can do maybe a injection, cementification, or maybe hazardous waste landfill. That you
Hazardous
have to
waste
take it.
Okay, thank you.
Okay.
What time is it?
With the RO,
11:03.
major plants you have there, how often do you have to change up those filters and where do those go?
You mean the reverse osmosis filters? Typically, they guarantee about 7 years of shelf life for but it depends on the other ones, other constituents like iron or any other water quality parameters are in present. Sometimes it might be like 4 years. So those ones, again, it's like similar. I mean, in the future, it might be has to go to hazardous waste landfill right now. Thank you.
Thank you, Dr. deSilva. That was a very good summary of some pretty big treatment systems for PFAS. Next up, we have Seth Kellogg. She's a principal geologist from Geosyntec from our New Jersey office. Seth has traveled down to Florida several times to give PFAS presentations. We appreciate you coming all this way. Seth is a PFAS industry leader. She's co-authored the first best practices guidance for the Natural Groundwater Association in 2018 and has briefed Congress on the state of PFAS science and policy. She's one of our go-to PFAS experts, and today she's going to talk about strategies for industry on PFAS usage and reducing risks and liability. Seth?
Good morning. I am going to take this in a completely different direction than the previous talk. So we're going to go back to a 40,000-foot view of how we think about managing PFAS risk and liability, particularly moving forward from where we are right now. So I've been working in PFAS for about 10 years now, and when we first started talking to our clients, this was the reaction I got. You know, why should I care? All of the regulations were focused on drinking water and receptors, and there really wasn't a whole lot of discussion about where this is going to go. And then things started changing. Over the last 5 years, we've seen regulations go more to point of use and effluent standards and trying to reduce PFAS. And at the same time, we're seeing a huge media campaign in everything from Trevor Noah and John Oliver talking about PFAS on late night to forever chemicals and dark waters and the devil we know, and it's really cast PFAS in a very different light, and it's changed the conversations that our clients are having about their social responsibility regarding PFAS. So the first thing we usually ask them is, where is their risk? And this is my representation of the PFAS vortex and how you get sucked into that PFAS vortex. It could be source water coming onto your site. Are you using a source of water that happens to have PFAS in it to begin with? Is there AFFF on your facility? Do you have processed materials? And when we ask these questions, we usually ask it around functional questions. Most people don't know if there's PFAS in their process, but most people know if their process requires reducing heat, reducing friction, reducing grease, heat resistance type of properties. So we usually ask these questions in regard to properties rather than specific chemicals, because we can help them figure out the specific chemicals. Is this going to be a discharge permit issue for you? Is there going to be, are there fish in the river next to your facility that, we have a fish advisory on now? Are you getting involved in litigation, either from the ESG perspective or from product liabilities? What are the regulatory requirements in your state? And if you have facilities across multiple states, how are you balancing those regulatory requirements? Is there an M&A component? Do you need to know what's at your facility for sale? And then what are your external factors? Meaning, what are your competitors doing? What is the community doing? What are the external factors that are impacting your risk decisions? So we usually start with the low-hanging fruit. AFFF, pretty much everybody has an understanding of where it is, and it's pretty easy to identify. There are definitely things, everyone talks about moving towards fluorine-free foams, moving towards water-based systems, but there are a lot of requirements and regulations that force you towards using AFFF, and not all of them have changed. If you're pipelines or power generation or a bulk storage facility, a lot of the regulations requiring AFFF are still in place. Also, there are state fire and building codes that are not changing as quickly as the NFPA codes are. And your local authorities having jurisdiction really do have the ultimate say over what you do. So we have a client that is a lessee of the Port Authority of New York and New Jersey. The Port Authority is not ready to move away from C6-based foams in their facilities. So they don't have options to move to fluorine-free foams or water-based fire protection systems. So again, we need to understand what the limitations are and the choices you have. Same thing with insurance requirements. There are insurance companies that will not insure your bulk storage facility if you don't have a fire protection system that they consider to be appropriate. And then you also have to evaluate the internal tolerance for large loss. So obviously the change that you have when you're moving away from AFFF. So for the NATA, in 2019, the NATA released a study that was done with the University of Maryland. And basically what they found was 2/3 of the AFFF releases were associated with accidental releases. And they all cost at least $750,000 to clean up. And so when we're talking to clients, they need to understand that there is a risk associated with having a foam system inherently, because these foam systems don't necessarily function the way they need to, or at least are not as predictable as one might think. And so is the risk of the fire more, I guess, important or concerning than the risk of having an accidental release at your facility? And what can you do about preventing those accidental releases? So we do talk about these AFFF system best practices. Foam storage, this is a big question we get, because a lot of these foams do tend to be chemical bulk storage issues. And different states have different regulations. So the foam that has the lowest regulatory burden in the state of New York may not be the foam that has the lowest regulatory burden in Michigan, because ethylene glycol is managed as a hazardous material in New York, but not in Michigan. So you do need to think about how that's going to impact your regulatory reporting and your permitting. We do talk a lot about containment systems. If your system goes off, where does it go? Does it go into the creek? Does it go into a retention basin? Do you have a containment strategy? Does it go directly to the publicly owned treatment works? We talk about how you can harden your foam system. Can you have redundant sensors? Can you have abort stations? We have seen situations where the foam system can't be turned off by the local personnel. It has to be the fire marshal. And once they find out it's an accidental, they've accidentally set off your fire suppression system, their urgency to get there may not be the same. We do talk a lot about fluorine-free foams, and it is an option in some cases. However, it does require some engineering and thought, both on the system side as well as the health and safety side. So these fluorine-free products tend to be more caustic than the traditional AFFF products. And so staff that are used to using AFFF in one way and treating it in one way may have different health and safety concerns with the fluorine-free foams. They also require about 3 times as much water. So that does require retrofitting of piping, and in some cases retrofitting of your water source. And then we also consider switching to water-only fire suppression systems. And now that the National Fire Protection Association has adjusted a lot of their guidance, particularly for hangars and things like that, those water-only systems are an option. So once we go beyond AFFF, what kind of questions do we get? And I put this slide up. You know, we're hearing a lot from our packaging clients. We're hearing a lot from cosmetics and personal care products, medical device manufacturers, carpeting, landfills. They really are looking at their supply chains and trying to understand where their potential liabilities are. And I put up this quote because it's from Heidi Greether from Michigan, and I think we've heard it over and over again over the last couple of days, but the only place that they're not finding PFAS are the places that they're not looking. So there is an expectation that we will find it in everything. However, we also get an equal number of questions like, I'm in the film industry, and film, according to ITRC, is listed as an industry that used PFAS, but I closed my plant in 1964. Did I use PFAS? Do I have to do a full investigation? And that's when we pull in our industrial archaeologists and our process engineers to really dig in and get an idea of when and how PFAS would have been used in specific industries. So, but the next question or the next discussion we have is you can't manage what you don't measure. And so you need to have an understanding of what the regulatory system is in your particular state or a suite of states where you have sites and facilities, and understand this evolution from point of use to point of release. We also need to evaluate the process and the PFAS usage drivers. So are there ways that we can move away from PFAS-containing materials? Or are there ways that we can isolate those materials? Or are there ways that we can look at the process and mitigate those factors? So for example, if you have to use a half a gallon of PFAS in your treatment or in your process to make your product, is blending that in with your 25 million gallon a day water treatment plant enough of a mitigation measure? Or do you have to think about other more targeted specific treatments at that particular location? We evaluate the storage, usage, and cleanup standards. So where is your material being stored? How is it being used? Do you have good housekeeping practices? And again, can you mitigate those releases? And then we evaluate the site setting. You know, obviously, if you have an on-site landfill or an on-site water treatment plant that's been there for 50 years, your liability or potential liability is different than it would be if you had a newer facility or you didn't have some of those on-site operations. And then we look at the impacted infrastructure. So are we going to need to change out piping? Are we going to need to clean out piping? There are great proprietary products now that can help remove legacy PFAS from existing piping. Or you can do a triple rinse. It just depends on where your liability is comfortable or where you are comfortable with the liability. So last week, EPA did release guidance on best management practices for pollution prevention and source reduction. They're pretty much what we would expect. So get the PFAS out of your process to the extent that you can. Have good housekeeping practices so that you minimize accidental discharges, and then decontaminate the equipment that you're removing your PFAS from. So the way we usually approach this is a risk analysis process where, again, we start with understanding what the regulatory framework is that we're working under. We want to understand how and where the PFAS are used in the process and whether we can isolate that or whether we can remove those or whether we treat those in a discrete way at that process. We evaluate the potential release pathways. So where are your receptors? How is the PFAS going to be getting to them? We consider, again, those external influences. We have a client who is in a community that is highly impacted by PFAS. They don't use PFAS in their process, but their source water contains it. How are they going to manage the messaging around, we don't want to treat water that we're not adding PFAS to, but now it's above the discharge standards. So you have to have these conversations and understand the perceptions around them. You always want to evaluate the cost of action and inaction. So we bring in our environmental liability team to really look at what those costs can be. and help us evaluate those risks. And then we apply a numerical risk assessment to make some educated decisions and to prioritize responses based on those risks. And I just want to emphasize that these things all need to be done in concert with your clients, and in particular with the facilities that these decisions are going to impact. Because if you don't have buy-in from the local staff that has to implement this, it can really be a challenge to make it all move forward. So that's all I have for today. That's my contact information, and if anybody has any questions. He's coming.
Excuse me, you showed a narrated lagoon out there at a wastewater treatment plant for an industrial site, and these may be 50, 100, 200 acres in size. Is anybody proposing to, especially if they're historical ones, been there 50 years, I mean the past 30 years, anybody proposing to clean those out to bottom?
We certainly have had discussions, and it really, I am not an expert in wastewater treatment, so I do want to preface these comments with that. But, you know, part of it requires an understanding of how you can maintain existing operations if you do want to remove PFAS from aeration ponds or clarifiers. And it does, you need to look at what's going out the end of your pipe, or at least as close to the end of your pipe as you're comfortable getting. With actually having data, so that you have an understanding of whether those things are required or not. Because if your inputs in your, you know, if everything by the time it gets to your on-site water treatment plant is so diluted by other process water that you don't have an accumulation of PFAS in your water treatment plant, then it's not as necessary. So you need to look at what the potential impacts are and how required that is.
I've got a quick question. Has the PFAS content of the AFFF, wasn't that required to change to take out PFOA and PFAS? And
Yeah.
I know they grandfathered in to use what they have left over, but.
So I guess I sort of put foam into 3 different buckets. So there is legacy C8 PFOS based foam that should have been, you know, grandfathered out before 2015. Or should have been removed before 2015. There are newer C6-based or 6,2-FTS-based fluorotelmer foams that have been used since then, and as of now, they're still technically legal. But what we've seen is if you don't fully clean out your fire protection system, you know, we're seeing, you know, part per million concentrations of legacy PFOS ending up mixed in with those systems. Because the piping wasn't cleaned out. So you change the bladder, but you don't clean out the piping. So it requires a little bit of thought, and it's a process.
Understood. Any other questions? Looks like people are getting hungry, right?
Yeah.
Sorry. Very good. Next up is Paul Newman. Paul is relatively local in Orlando. He's the DoD Market Sector Lead for ECT2 for emerging contaminants and PFAS. He specializes in developing treatment technologies and currently focuses on synthetic media technology for PFAS and 1,4-dioxane. Today, Paul's going to discuss ion exchange regeneration. So, Paul, take it away.
Thank you, Joe. Very happy to be here in front of all of you. As I looked through the agenda for the proceedings this week, I think I win with the longest title of any presentation here. But whereabouts is there we go. What my presentation is really about is waste minimization. That's what I'm going to talk about. I'm going to talk about a strategy that can be deployed wherein you can take 1 million gallons of a dilute waste stream and concentrate it to 1 gallon. So it's really about that concentration step that Viraj had mentioned earlier in his presentation. So once you can concentrate the waste to a really high factor, then you can enable discussions about, well, how are we going to destroy this waste? Or where is this waste going to go? If you're dealing with a highly concentrated waste, what you do with it, where it goes, they're much less of a consideration. So let's get started. So if we talk about that 1 in a million concentration step, I'm sure everybody in this room has regaled their families around the kitchen table, right? Well, what's a part per billion? And you bring up the Olympic-sized swimming pool scenario, right? So if we look at that concentration factor of 1 million to 1, what does that represent? So the first scenario, so if you have an Olympic-sized swimming pool and you add half a gallon of water to that, what do you end up with? Well, you end up with about 500,000 gallons of water, not surprising. Scenario 2, what if instead of half a gallon of water, you've accidentally added half a gallon of PFAS to that swimming pool? What do you end up with now? Well, you've got a problem, right? You should probably change your pool company, first of all. But now you have 500,000 gallons of PFAS-containing liquids that you need to deal with. That could be a hazardous substance if the regulatory path continues. That could be, in future, a hazardous waste under RCRA. So that's a tough scenario. You've got this big 500,000 gallon swimming pool to deal with. So what if we could put the PFAS genie back in the bottle? What if we could take that 500,000 gallons and put it back to its original state? So we have a technology we're using regenerable ion exchange where you can actually do that. We can take that 500,000 gallons and concentrate it back to half a gallon. So that's what I'll talk about in more detail today. And what that does, that concentration factor really does set up, it minimizes obviously the amount of waste that you're going to be generating. It reduces your overall life cycle costs because you're not transporting waste and your operational costs are actually lower. And what that does is sets up concentration for future destruction technologies. So that's what I'm going to go through today. So I'll talk a little bit about who ECT2 is, a little bit more on PFAS impacted waste streams, kind of what the typical go-to technologies, many of which have been discussed in detail during this conference. And then I'll drill down to a couple of case studies involving regenerable ion exchange and how that strategy has been deployed to minimize costs. And I'll talk about what the impact of those are on actual life cycle costs when you consider, say, a 20 or 30-year time frame, because the savings get to be pretty considerable over that time frame. So ECT2, the name stands for Emerging Compounds Treatment Technologies. The company was formed approximately 2015, and we are basically a solution provider for treatment technologies. So I'll start off by saying there is no one treatment technology that is the silver bullet out there, particularly for PFAS. We've been doing this since 2015, initially focused on 1,4-dioxane, but then transitioned to PFAS very quickly. Often the solution is a treatment train, and every site is different. Every site is different. Depends on water quality, what your treatment goals are, what your client goals are, what the schedule needs to be, what sort of risk you're trying to mitigate, whether it's off-site receptor risk. Every site is different. So we have a team very focused on R&D that can help develop solutions using influent water quality data, and then we can kind of bring it full circle through supplying a system, operating system, if that's the particular need. But we treat a variety of different waste streams, groundwater, surface water, landfill leachate, and we deploy a number of technologies, some of which I'll talk about. Foam fractionation is a particularly interesting one that can be used as part of a treatment train. So often it is a treatment train approach that's deployed to address any one particular issue. We talked about granular activated carbon a little while earlier. Well, often we use that as a pre-treatment step going into an ion exchange system. So I'll talk a little bit more about that in detail. So if we look at ITRC, a reference that many of us in this room use, if we look at the state of ex situ treatment technologies, and I'll just talk about ex situ, not technologies that are in situ. So if we look at the water treatment options that are out there, the field implemented treatment technologies using ITRC's category of field implemented versus limited application or developing technologies. If we just look at the kind of go-to ones, it's really, the big ones are ion exchange resin, whether it is single-use resin or regenerable resin, and granular activated carbon. Again, these are many times they're used in series or as part of a single solution. If we look at a comparison of those two, primarily of granular activated carbon versus ion exchange, whether it's across the top we have GAC, single-use ion exchange, and then regenerable ion exchange. And I'll get to, well, what is regenerable ion exchange? So if we look at the different technologies that are available, we've heard in previous presentations the effectiveness of granular activated carbon, very high for long chain compounds, a little less so for shorter chain compounds. Ion exchange, particularly effective for both short and long chain compounds. And the nature of granular activated carbon, you basically need to have water in residence with that granular activated carbon media for a longer period, so that's empty bed contact time, if you're not familiar with that term. Whereas ion exchange, you end up with more rapid kinetics of the reaction, so you can end up with smaller vessels using less media. And then just kind of scrolling down, if you look at the waste generated, granular activated carbon uses larger vessels, so you could potentially end up with a larger amount of waste that you need to deal with. Whereas ion exchange, single use is smaller, regenerable, it's really negligible. So I'll dive into what is regenerable ion exchange now. So what we have is a technology, and bear with me, the pointer here. Oh, there we go, it works. So if we consider that vessel right there as your treatment vessel. So water comes in the bottom of that treatment vessel, your influent water, and it goes out the top and it's treated. So that vessel is filled with single-use or regenerable, in this case it's regenerable ion exchange media. So once that media gets saturated and you start to detect breakthrough through your sampling program, what happens, you actually take that vessel out of its lead position. They're typically both arranged in a lead-lag sort of configuration. You take it out of the lead position, and then you, in a counterflow direction, you actually take this regenerant solution and you pass it through that vessel in a counterflow direction, and effectively what you're doing is you're stripping the PFAS off of that ion exchange media. What we then do with the regenerant solution is that is distilled down to a very small volume, and we create still bottoms. Those still bottoms are in the range of, that's the concentration factor we get to taking 1 million gallons of influent water to 1 gallon of still bottoms. The still bottoms can be applied onto a solid media that can go for disposal or incineration, but often much of the still bottoms that we've been creating at some of the sites are used by various research institutions right now to try out their destruction technologies. So we're working with Clarkson University, several other providers of destruction technology, because they need that concentrated waste to make destruction effective. Here's an example of where we've done this. This was Pease Air Force Base in New Hampshire. We have a treatment system that includes a regeneration treatment system through ion exchange. That's on the top right. And then on the bottom right, we have a distillation unit. So the influent concentrations are pretty stout here, not unlike many fire training areas, 50 to 100 micrograms per liter. And we designed the system to operate at up to 200 gallons per minute. So it's a regenerable ion exchange system. And to date, we have treated 50 million gallons of waste at this site. And we've had clients out there, and we show the system, they say, well, where did all the PFAS waste go? And we point to the corner of the room and show them, well, all the waste that's been generated are in these 2 vessels since 2018. So where's the waste gone? The waste gone's nowhere, it's still on site. So by the time everybody figures out, well, what destruction technologies are going to be applicable for destruction at commercial scale, that's what you can do with that sort of waste. But the idea is, operating this in 4 years and no waste has gone off site, the economics of that particularly become attractive when you look at this on a larger scale. So what this means, again, if you have this particular sort of system and you were to compare it to this was a pilot study and a life cycle cost analysis that was done by an outside firm comparing single-use granular activated carbon versus regenerable ion exchange. So on the right-hand side, you can see if a system that would originally was going to just be granular activated carbon was installed, they would have generated, based on the influent characteristics and the particular nature of water chemistry at that site, they would be generating 185 drums of granular activated carbon per year in perpetuity, basically. We all know pump and treat systems are not a short-term game, right? So you take 185 drums, and if you consider the network of military installations and how many sites they have where they would be otherwise generating 185 drums per year, the numbers get pretty big pretty quickly. So having an alternative where they can just, have minimal amount of waste, the economics work out very, very well. So how this works is you've seen the system on the left. So that's what we have installed at Pease Air Force Base, that permanent system. But if you think more broadly about how this could be applied in a different sort of scenario, you can actually have multiple treatment systems that are just the treatment components of them, and then once those resin vessels get saturated, they can be located, moved, transported to a central regeneration location. So if you had multiple military installations within, say, the state of Florida, and you had a central regeneration plant, well, that spent media can be transported, and really all you're doing is transporting, for that sort of situation, you're only transporting the vessels like this. These are 42-inch vessels that contain regenerable ion exchange media. That's what gets transported. Back to the regeneration facility, the regeneration process takes about a day. The frequency of regeneration could be once every 2 weeks, could be once a month or so, but typically you have extra vessels kind of in your store at your treatment system site. But that's how a regenerable sort of solution can work. And we've actually done this in Australia. ECT2, kind of after this Pease Air Force Base project we did, the folks in Australia were very interested in the potential application of this. So they have a large base in Southeast Australia, Williamtown, where they had multiple areas that were impacted by PFAS. And so they were very concerned about transporting waste across lines of their territories. There are particular rules about doing that in Australia. And so we talked to them about how we could employ such a strategy at a single base. So we did this. They had already defined the nature and extent of PFAS impacts. They already had Aaron Brockovich out there, so the people with the pitchforks and torches were already raising the flags. We want something done. And Australia was very quick in terms of establishing health-based guidance values. They did that very, very quickly, back in 2016, I think it was. So they asked us, well, what would a configuration look like? So what we ended up doing, there are, it's a little hard to see here, but this kind of gives us that. This is a big plume. So the red boundary is the base. You have off-site impacts going to the south, what they call the southern area. You had surface water impacts going off to the east from the Moores Drain area. And then you had a former fire training area. So lots of problems. So the approach to doing this was, we originally kind of did a pilot project treating stormwater at Moores Drain. Then in the second stage, we treated groundwater at former fire training area, and then treating groundwater that flows off-site. So the idea, of course, was to mitigate the risk to off-site receptors, remove mass from the PFAS source areas, and really minimize the amount of waste generated and meet the Australian health-based guidance values. So the way this looked is that we have Moores Drain, that's a surface area water treatment system here. We have the southern area, which is a treatment system that draws water from down here in the southern area. A former fire training area here, and then the regeneration plant is here. So everything is on the base, right? They're not transporting it from one base to another, not transporting waste across lines. So the idea is that the central regeneration plant services all three of those treatment systems, and then we distill the concentrate there, and then water is able to be discharged back on site. So the Moores Drain site, this is kind of an interesting one because we sent a Connex box in the Antonov aircraft that unfortunately just got trashed over the Ukraine. We actually had that out in Maine, and they transported several of our Connex boxes with our systems over to Australia. So we originally started with this small system here on the right, and it was just a 50 GPM demonstration project. Very quickly they said, okay, all right, we need to ramp up the scale. This works, we're convinced, let's do it. And working in Australia, that sort of climate, you can get away with, all right, we're going to ramp up the scale to 130 GPM by adding tanks on the outside, by putting in additional piping, and we were able to get that to 130 GPM really, really quickly. So, we obviously learned treating surface water, pre-treatment's a big, big thing. You have, in addition to your usual iron problems, we had eels and all sorts of other things in the influent. It was a problem. But the performance data graphs I'll show for the different areas, they all pretty much look the same. The influent here was 2 to 10 micrograms per liter, and we've consistently been below the health-based guidance values. And at the former fire training area site, you can see, these systems all look the same. We basically, have pretty standardized designs for these systems in Connex boxes. And the concentrations here in influent was, 10 to 500 micrograms per liter. So a very similar system. This was an interesting site. We got involved at the site where there was already an existing granular activated carbon system to treat surface water. They were treating at about 190 gallons per minute. They were generating in the order of 914 tons of waste. We looked at an alternative, put in place a regenerable treatment system, and we're treating groundwater at this location. These photographs are literally like 300 to 400 feet apart at the base. And so we've only generated 7 tons of waste, treating basically the same influent concentration, same sort of flow rate. And this basically shows the same thing. We've been below health-based guidance values in our influent, actually between 15 to 55 micrograms per liter. So pretty stout concentrations. And then the southern area, again, the systems look very similar. Concentrations were pretty high. And we co-located that with one of the other treatment systems to share utilities, reduce O&M costs, and we were able to discharge treated water back to the site. And again, we've been consistently below health-based guidance values, and we've been operating these systems actually in Australia. The Australian government wanted to just stick with us for O&M, so we've been providing that service since 2016 in Australia. So how that kind of equates to what do life cycle cost comparisons look like if you were to deploy different technologies. This isn't the Australian example, this is a different example, but the cost curves are kind of the same. If you were to look at, say, a 20-year, that's what this axis is on the bottom, life cycle cost, if you're generating a lot of waste, obviously you have an upfront capital cost, but your operating costs are pretty high over a longer period. Whereas if you put in place like a regenerable ion exchange system, where you may have the additional cost of that regeneration plant, that pays for itself right around this point, probably in the 5 to 7 year time frame. That's where the curves cross. That's where it really becomes economic. Regenerable IX technology is not the be-all end-all for every solution. Fire training areas works really well where you've got high concentrations. And if you have multiple sites that may need treatment systems and you're looking for central regeneration, then the economics become much more compelling. So the takeaways we learned from Australia, regenerable ion exchange works really well, high capacity, and they were able to reuse water on site, and we met consistently the health-based guidance values and greatly reduced waste, which again, if you recall, was one of the client's primary objectives. So in terms of getting to the next stage of destruction, what makes that applicable? Well, as we've heard before, you've got to concentrate the waste. Membrane, you can still end up with an RO concentrate if you were going to go the RO pathway, and it can be a large volume. Foam fractionation is a really interesting technology that we sometimes use as kind of a pre-treatment step, and sometimes independently. We've seen like 95 to 98% removal efficiency just with foam fractionation. So the main thing we deploy is a solution that can include regenerable ion exchange, but again, often it's a treatment train approach. And that will get to the point where PFAS destruction becomes applicable. So with that, that's my presentation. I appreciate your attention today, the opportunity to be here. Thank you. Any questions?
I was a little surprised by your economics at the end there, with GAC being so much more expensive than either single or regenerable ion exchange resin.
Right.
Do you have a similar curve that shows concentration, as a function of concentration? I mean, I just know that for a lot of the engineering firms spec out GAC systems because of cost, and it seems like based upon your numbers, it's way, way more expensive than ion exchange. I was surprised by that.
I think it can be a function of what sort. Do you have shorter chain compounds? Do you have longer chain compounds? Right? If you got shorter chain compounds, you're gonna blow through carbon more quickly. So yeah, it can be a function of concentration and speciation of the PFAS compounds as well.
Yeah, but they're not regulated yet. So I mean, I guess I'm just trying to figure out the economics of the GAC, right? Which is also regenerable, right, thermally. So
sure.
Why is that so? On a cubic foot basis, ion exchange resin is way more expensive than GAC.
It is.
Right. So I'm just curious, where did those numbers come from? I mean, how'd you do the economics of that, showing this? I mean, there was huge differences there, obviously. No one would ever choose GAC based upon the graph you just showed.
Yeah, this was done by Weston and Sampson, I believe. It was an outside party that looked at the initial data that came in from Pease Air Force Base. So that's where the original data came from. Yeah.
I have a question about slide 24.
I don't know which one that was, but want me to back up?
Great, yeah.
What was it regarding?
No, he's not looking. No, the guy behind. You need to talk.
David?
Okay.
Oh, he's working on it. Okay.
In any case, you're showing the amount of waste for the carbon and ion exchange resin.
Yeah.
They were very different numbers. Just to clarify, that's not 24. That's maybe it's 23, one before it. Yeah.
That one.
Sorry. So very different numbers, and I just wanted to clarify the waste that generated here.
Yes.
Is that the concentrate after regeneration, or is it the actual amount of carbon or ion exchange?
Yeah, in this particular case, what we were generating is the amount of still bottoms, the created liquid waste, which in the case of Australia, what they're doing is they're taking those still bottoms and they are at a very low flow rate. They are passing them through another solid media, which is called our superloading process. So that is a solid waste that is generated through that process. If you don't go down the destruction path, that's kind of what you end up with, comparative to granular activated carbon.
Thank you.
Okay. Well, thank you very much.
Thank you, Paul. Last but not least, and then we got to go to lunch. We're a little bit ahead of schedule. So Dr. Tamzen Macbeth is a Ph.D. in PE from CDM Smith. She's the Senior Vice President of Remediation and Remediation Practice Leader. She's published over 100 papers, presentations, training materials, and is also an associate faculty member of Idaho State University. So appreciate you coming all the way out to Florida, and she's going to talk about advances in high-resolution site characterization technologies and applications for PFAS.
All right, thank you everybody, and thanks for hanging in there. We should maybe do the 7th inning stretch. We're almost to lunch, so I'll try to get through this material relatively quickly because I realize I am standing between you and lunch. So I kind of want to take a step back and talk about how we construct remedies. And a fundamental tenet in remediation is to begin with the end in mind. And that really is, we want to clean up sites and we want to close sites. And our ability to do that is really contingent on developing really effective conceptual site models that help us understand how contaminants are distributed in the environment, how they impact receptors, how we can select technologies. So this conceptual site model is really the foundation that allows us to do things like evaluate remediation, develop characterization strategies. And so I want to step back and talk about this in the context of PFAS assessments, because there's a lot of things about PFAS that are really different than other contaminants that we've spent decades evaluating. So there are things that are similar about PFAS and how we build a conceptual site model, things like understanding nature and extent of contamination, understanding soil stratigraphy and geology, understanding geochemical conditions, understanding contaminant mass flux. All of those things are very similar when we're building our PFAS conceptual site models. But a couple of the things that are very different are understanding sorption and sorption characteristics of PFAS. So I'm going to talk a lot about that today. A couple of parameters, things like ion exchange capacity become really important when we're talking about sorption of PFAS, and the air-water interface, which a number of folks have talked about today. So I'm going to use the conceptual site model of an AFFF release as the concept for how you build a CSM for a PFAS site. So it's important to understand that how AFFF and PFAS partition once it's spilled onto the surface in the subsurface environment must account for several what we call compartments. So it's really understanding how those chemicals are sorbing onto the solid soils, how they are dissolving and migrating in pore water. A unique element of PFAS, because they are surfactants, is the fact that they actually partition to air-water interfaces. And so that needs to be accounted for. And then if you have other contaminants like NAPLs, the partitioning into the NAPL must also be accounted for. So you essentially have these different compartments. We've got air compartment, water compartment, soil compartment, NAPL compartment, and we need to account for the sorption characteristics within each of those compartments to understand the flux of contaminants. How are these contaminants moving from, say, a Veda zone to groundwater to understand things like leaching? And there's a lot of complexity to that. So I'm going to take a step back. Zoom talked about this in his presentation. We talked about different characteristics. Chad this morning, when he was talking about GAC sorption, a lot of the sorption guidances, including the EPA guidance, use this concept of evaluating total contaminant mass and evaluating the relationship between the mass sorbed onto solids and the mass sorbed to water. So there is this technical guidance. You can get screening parameters to define these important sorption characteristics, this KD, which defines the percent of mass that's going to be on the solid versus the percent of mass that's going to be in the pore water. All of these guidances and models that we're using assume linear sorption isotherms. They do not consider things like desorption generally, and that is going to be important. I'm going to talk about that a little bit. And they do not account for things like the air-water interface. So what does that mean for PFAS? Well, I'm going to talk about Florida for a minute, because we're all in Florida. And Florida has released these provisional soil cleanup target levels for PFOS and PFOA. And so this is using a calculation that's very similar to the EPA guidance. It's in the FAC 62777. And when they go through the standard process of evaluating KDs for PFOS and PFOA, they're getting these soil cleanup target levels on the order of like 2 and 7 micrograms per kilogram, so pretty low levels. Now, there was recently a paper published by several folks in EPA, both with the Environmental Cleanup Group, EPA Region 2, EPA Region 3, and the New Jersey DEP, that is a review paper on using this EPA guidance to calculate soil cleanup levels. And so they went through, they took 18 case studies, and they evaluated KDs, the estimated KDs with laboratory and field data for a whole suite of PFAS chemicals. And one of the things that they noticed that they make a really good case for is, well, when you apply this standard screening process, the KD values that you calculate span 3 to 4 orders of magnitude. So when we start looking at relationships or analogies, things like chlorinated solvents, you can go out and because they're hydrophobic, you can estimate KDs very often using the organic carbon partitioning coefficient, and you get linear relationships that allow you to model that with reasonable accuracy. When you get data like this, where the KDs are spanning 3 to 4 orders of magnitude, then you start to say, well, what's really feeding that? Because that does not allow us to use this same process to calculate these soil cleanup levels. So I'm going to focus on PFOS just to exemplify that. So generally, you take a groundwater concentration, in this case, something like 70 parts per trillion for PFOS. If you apply this range of KD values to estimate soil cleanup levels, the range would be anywhere from 366 to 6,460 nanograms per kilogram. So when you're talking about how much removal do I have to do, this is a huge range. And then just for reference, again, that FDEP provisional cleanup target was 7,000. That was assuming a dilution attenuation factor of 20. And so, their range is down here in the kind of very conservative, like 350 is what that would translate to. The other thing, so this basically means that depending on your assumptions, using this standard method, you could be overestimating the amount of mass that's partitioning in that pore water and driving those soil cleanup levels by 100 to 1,000 times. The other important element is that when they looked at the field data, both field and laboratory data, that the KD, or that sorption coefficient, the desorption coefficient was an order of magnitude greater than the original sorption. What that means is that you have a lot of mass, particularly in field systems, that's irreversibly sorbed, and that's not accounted for in these estimates. So the Department of Defense has recognized this and has actually funded a whole bunch of projects looking at how you can evaluate leaching. And Zoom went through a bunch of work that a colleague, Charles Schaefer, and he have been doing for CERTIP and TCP, and he went through some of these equations earlier, so I won't belabor it. But again, it's okay, well, here's the traditional approach. EPA is saying there's problems with this. We're recognizing there's issues. What if we revise the approach to add this term, which is a term that accounts for the air-water interface? Does that help us define these parameters better? Again, the premise is that by neglecting this air-water interfacial sorption, you're going to end up with soil screening criteria and cleanup levels that are very conservative. The other significant issue at a lot of sites that was actually exemplified in Florida DEP's recent publication, where they looked at dry cleaners as a potential source of PFAS, particularly in the spent solvents, because what was happening is those spent solvents were essentially extracting PFAS out of all the waterproofing in the clothes, and then entraining PFAS that gets released along with those other spent solvents in affecting groundwater systems. So now, in addition to the air-water interface, which we'll go back down here to our equations accounting for that, when we're looking at the NAPL phase and potential partitioning into NAPL, we also need to account for that partitioning in the conceptual site model and in evaluating these cleanup levels. Jennifer Field at Oregon State University has been doing a lot of work, and they recently published a paper on these PFAS-entrained NAPL emulsions that form, and so that, again, can add complexity to your conceptual site model. So what can you do now? You know, there's a lot of sites that really want to be able to assess sites, to collect data. How do we define things like soil cleanup levels? This is actually a paper published by Hunter Anderson with the Air Force. Hunter's been very involved in all of this CERTIP and ESTCP work. He's also been overviewing a lot of the Air Force's PA, SI, and RI, so he has a very high-level view on what things seem to be working and what things are not, and he published this paper for making a case to directly measure soil to groundwater concentrations. One of the key things that he promotes in this paper is to take direct measurements of pore water using things like suction or drainage lysimeters. So Zoom talked a lot about that in his work that supports this concept that, look, getting these parameters is really complex. We're probably years to decades away from being able to come up with models where we can predict this. So I think in the near term, we're really going to be relying on these empirical methods for quantifying these characteristics. So I'm going to digress just a little bit now to talk about high-resolution site characterization. We actually recently published a guidance document for the Air Force in developing robust CSMs and using high-resolution tools. We developed a compendium with over 60 high-resolution site characterization tools that includes Excel-based tools selection table that allows you to put your data quality objectives in and to essentially get a suite of tools that you can use to quantify parameters in your site. So if you're looking at Vadozone for PFAS and AFFF, you might be interested in soil moisture, in geologic lithology, in organic carbon concentrations. So you can put those parameters in this tool, and it will actually give you different types of technologies that you can deploy in your characterization program that will fulfill those data quality objectives. The tool also has hot links, so if there's tools that come up that you don't understand, you can click on those hot links, and it has fact sheets that tell you all about what the tool is, what it does, and then actually has comparison tables, so all the different tools that might give you similar information, say on lithology or on hydraulic conductivity, it does a comparative analysis. So it says these are the tools you can use, these are the costs for the tool, this is the benefit, this is, can you go out and get it from a commercial vendor, or do I need to partner with an academic to get this tool applied? And what are the disadvantages and limitations of the data that you get? So it can be a really good way as you're building your characterization program to make sure you're really bringing all of the tools, or considering at least all of the tools at your disposal for getting these parameters to build better conceptual site models. So I'm going to go through and reiterate a couple of things on a case study. This is the case study that Zoom presented earlier, but I'm going to talk about it in a little bit different light. Looking at these high-resolution concepts for understanding how AFFF migrates in vadozones and how it affects leaching to groundwater. So I'm going to reiterate, Zoom presented this earlier. So the first thing to understand in the value of high-res site characterization for PFAS is that when we look at these AFFF sites, what we're seeing is that if you look at a vertical profile where you've got soil borings and you're collecting here samples on like quarter-foot depths, right? So really high resolution where you're collecting those samples, what we see is that when we look at the concentrations, the majority of concentration and mass is actually generally relatively shallow. So by taking that high resolution data, we can understand what the mass distribution is within that soil profile, both in the vadose zone, and then if you extend it here below the water table, you can get a similar profile. In addition, here we link, right, here's this soil sample collected, then we come over here. This is the composition of PFAS. So now you can start to see, and Zoom highlighted this, this transition when you go from high mass area where you have PFSAs that are dominating the PFAS profile, then as you migrate vertically down that soil column, you start to see some of these other things like 8,2-FTS pop up. And that tells us that there's some transformation occurring along that migration route. So again, in the field test, in this case, they were looking at leaching to groundwater. So they were simulating, right, with sprinklers, 22 years of infiltration through the vadose zone to quantify the absorption characteristics and the flux of PFAS to groundwater. I'll just reiterate this quickly because Zoom showed these data. They collected lysimetry data and basically were able to show that the lysimeter pore water concentrations were very consistent in the different depths. So here in the red, we've got the shallow lysimeters, and in the deep. So that suggests that a lot of that mass that was entrained in the pore water, right, occurred at the shallow depths. That was relatively conserved as you went deeper in the vadose zone, discharging. In addition, when we look at the sampling and analysis, here we have measurements of pore water concentration. So this is the lysimeter, this is PFOS here, the measured concentrations. When we calculate what we would estimate the pore water concentration to be and not account for the air-water interface, so using the standard EPA guidance, right, this is the concentration that we would predict. Which is obviously a lot higher, again, than what we actually are able to measure in the field. When we account for the air-water interface through quantifying it in the bench studies, we get a predicted pore water concentration that's much more in line with what we actually measured in the field. And that was really true or more consistent for PFOS and PFOA and PFHSX. So this is some data that extends, I would say, the presentation that Zoom gave, and essentially this is the fraction decrease in PFAS pore water concentrations here as a function of the total mass removed. So basically we're looking at, as we're flushing all these pore volumes through the system, we're removing some mass, and you would expect to see some reduction in pore water concentration. And what they saw is that even at very low, levels of mass removal, here we start to see, say 10%, 20% mass removal, we're actually seeing 40, 50, 60% reductions in the pore water concentration. So what that tells us is even modest levels of mass removal in the vadose zone have big impacts in that pore water concentration that's leaching to groundwater. And when we look at the fraction decrease in pore water as a function of total mass removed and extend that out for things like PFHXS and PFOA, we see very similar trends. So what does this mean? So if we go all the way back and say, okay, well now let's predict the pore water concentration, but let's use what we're measuring in the field to recalculate our soil cleanup levels now, what would that look like? And here we have, assuming, again, the groundwater standard of 70 part per trillion, dilution attenuation factor. And essentially, if we do that calculation, it would give us a cleanup level, a soil cleanup level of 1 million nanograms per kilogram compared to, again, the FDEP provisional cleanup level of 7,000. So you can see how understanding these site-specific parameters, accounting for the properties of the PFAS, accounting for mobility of the PFAS is going to be really important in order to define cleanup levels that are really commensurate with the risk that's being achieved with that release. Just briefly, I'm going to just touch on, there's also other high-resolution tools, things like passive flux meters. We've been working for decades with Mike Annable at University of Florida. He's developed chlorinated solvents. Originally, I think the first project I worked with him on was in 2000 at a chlorinated solvent site. But they're basically a granular activated carbon that's impregnated with tracers that you stick down a well. You have groundwater that flows through that carbon, and the rate that contaminants sorb onto the carbon is related to the contaminant mass flux, and the rate that the tracers desorb gives you estimates of Darcy velocity. So he has been working on modifying this technology for PFAS, and he's been looking at a whole variety of both granular activated carbon, but again, as has been discussed here, carbon has only limited effectiveness for the short chain PFAS, so they've been working a lot on using resins and other things. They kind of have a combined GAC and resin system so they can get these PFAS flux estimates. And this gives you just an example of what that data looks like, right? You get the sock that you deploy down the well, and then you get estimates of Darcy velocity here in blue, along with, in this case, estimates of PFOS flux. And so that can be really useful, again, when we're trying to quantify, okay, we've got discharges occurring in groundwater, what's the flux going off-site? One caveat is that it's some of the resins that they're using when we look at the negative control, those resins can have a background of PFAS. So we're seeing 6,2-F2S come out depending on the type of resin. So some careful consideration needs to be given to the design of that process and the resin used. So in conclusion, this leaching to groundwater studies are ongoing. There's just a huge body of work being done by a whole bunch of folks. But collectively, it suggests that a lot of the current guidance is problematic when we're developing soil cleanup levels. Collecting these empirical measurements of leaching flux and groundwater flux is likely going to be the most practical means in the short term. And that building these robust conceptual site models, particularly for source areas, can be improved using the concepts of high-resolution site characterization. So with that, I want to recognize there's a lot of folks that have contributed to the work that I presented today, and I think we have a few minutes to maybe take some questions.
So I'm curious, we know with chlorinated solvents, clays play a big role as kind of a reservoir of those things. Do you see anything similar with PFAS? You know, if you have clay soils, that it sort of gets bound up in there and releases a little bit differently than in organic materials?
Yeah, so a couple of things relative to PFAS. So actually the EPA paper does a really good job. So one of the things they were trying to do is correlate or do regression analysis to understand what parameters were really driving the KDs. And one of the things they looked at was things like cation exchange capacity. And their regression analysis did show that actually one of the significant things that affected sorption was clay content. And that's why, because that surface reactive, PFAS with the clays do tend to affect sorption of particularly some of the PFAS. There's also sort of on the flip side this concept that the air-water interface also really drives PFAS sorption. And so there's been papers published, Hunter Anderson actually was co-author on one of them, that talks about clays, because clay is retains water, right? It has a much higher water saturation, typically even in vadose zones because of its structure, and so it has less air-water interfacial area. So there is also a conceptual site model out there that PFAS migration pathways are almost the opposite, where you get higher air-water interfacial sorption in transmissive like sands and gravels, where you have more surface area versus clays. So clay is definitely a big player in the characteristics of sorption and transport of PFAS.
I guess I'm trying to understand the actual mechanism. Does the PFAS chemicals have anion charge?
So they have all of the above. They have positive, you've got cationic, anionic, and you have zwitterionic, which have properties of both. So that's part of the reason why the sorption characteristics are so complicated, because depending on the suite of PFAS you have, they exhibit all of those.
Okay. Soils have a very low AEC, anion exchange capacity, yet we seem to see that the PFAS chemicals stick to the soils and the surface for some reason, and they have a much higher cation exchange that absorbs the cation end of it. So are we looking at a chemical that's got a positive and a negative end, and it attaches to the soil particles in that exchange reaction, or are we looking at entrapment of these large compounds?
Again, I think there's probably some aspect of all of the above, especially for things like AFFF, where you've got complex mixtures of PFAS, right? There has been a lot of work looking at things like precursors and long chains, and we're definitely seeing a lot more retention of those in those shallow soil zones. So that may be something more like entrapment, right? They're much larger molecules, whereas there may be, the short chains and more mobile components like PFAS, may behave very differently. And in that case, there were several in the EPA paper where the cation exchange capacity did correlate in the regression for certain PFAS. So, and that was the mechanism that they suggested.
I still see it sticking up the top, and generally, if we had to make a real general assumption, there are soil organic matters up top there, and as we go down into soil, in some soils, we may pick up more clay content, but it seemed like it still stuck. It wasn't evenly distributed, in soil depth. So it looks like the organic matter sticks to it, it sticks to organic matter.
So there is also, in the regression analysis, they assessed it relative to organic carbon. They found that there wasn't a correlation with organic carbon for most PFAS, with the exception of concentrations that were greater than 5%. So if there's a lot of organic carbon in the system, then they were seeing the correlation with the sorption, but at less than that, at lower organic carbon concentrations, they were not. The correlation was not significant.
Other questions? All right. Well, thank you, panel.
Yeah, a big round of applause for all four presenters.
We are going to break for lunch. It should be rolling out here in just a few minutes, and then we're going to wrap up. We've got one more session to go this afternoon, so enjoy lunch, and we'll be back.
I got that from your bio.
Yes. So they just published